networks is something like this network here or there, and this is two-dimensional, this is three-dimensional. It's just for understanding what we have in this, and of course in reality we have many other networks. And the idea to manage such kind of stuff came to my mind when I was in Italy and I visited some fishery port, and I see a real fishery network and see, look, it looks very nice. From how can I model this kind of stuff from the point of view, and I see how it looks like. There is some joints, and joints are rigid, and some very flexible fibers connected. Can we do something for this just from, let's say, this point of view? And there are some pictures of such a network. And what I would like to underline you have some kind of, let's say fibers. Here you have steel fibers, they somehow connected. And these connections, in this case, for example, looks like a symmetric, but this is not so because this is a point of connections is not symmetric, and also you see here that usually is not symmetric with respect to let's say axial lines of fibers. It looks like that. And such kind of networks, technical networks, are very used, for example, green facades in some countries and so on. There are a lot of such stuff which we have. In reality, this picture was taken from the prospect of one German company producing this stuff and so on. This is typical network which you can see. And if you want something more complex, let me remind one of the previous presentation about forms and open cell forms, exactly this example of typical network. What we are doing now? Now we would like to discuss such structure within framework of Cassara continuum. Let me discuss what is a Cassara continuum is. It's just for some very short introduction. Here we have two kinematically independent fields, field position vector in actual, in current placement and reference placement time, and vector of so-called tensor of micro-rotation. This is orthogonal tensor, which also depends on this. So we have two kinematical fields, 2 degrees of freedom related to translations and rotations. And this is a representation of using Keringen's approach. You can say that this Q is just a sum of directors of 3 directors in reference and current placements relatively. So we have kinematics. Then we introduce the strain energy. We discuss elastic case. We introduce the strain energy following equipresence. Everything depends on everything. So you have that gradient of this. And gradient of orthogonal tensor is became third order tensor, but it's not, let's say, very convenient to use it. Moreover, it's not fully independent. It could be reduced to the two strain measures, which both of them non-symmetric second order tensors, which is written here, and something we discussed it in this paper, which came also from natural observations that some people using different strain measures in Cassara continuum. So, okay, so we have these two strain measures. Okay, this is constitutive equations which we have. Now let's see what we have in the case of dynamics. In the case of dynamics, we should introduce kinetic energy. Kinetic energy, in the case of Cassara continuum, general form looks like that. It's a quadratic form of velocity, linear velocity and angular velocity, which is defined like that. And so you have quadratic form, and this quadratic form we have density, material density, and we have two tensors, second order tensors, which are called micro-inertia tensors. Usually, for example, for many problems, people telling that J1 is disappeared, it's vanished, and J is just a spherical part of the tensor, it's just one scalar measure of inertia, and that's it. Now we will see the idea of, let's say, nearest future is try to understand how we can derive previous energy and this, let's say, for effective Kossara medium for our elastic network. Okay. If you consider it Kossara continuum, we have equation of motion, and the equation of motion looks like here. We have stress tensor and couple strength tensor. This is Lagrangian formulation. We have forces and couples, and we have inertia terms here. And you see that if these J tensors are not zero, you have rather, let's say, complex form. But this is, if I forget about the left parts, I mean tensors of stresses and couple stresses, it looks like equations of rigid body dynamics. Okay, now as I'm speaking about networks consist of fibers. Fibers looks like a line, some curves. I will introduce something which is called Kossara curve model. Roughly speaking, its Kossara curve model is a one-dimensional Kossara continuum. We have reference placement with three directors. Now this directors is a function of Lagrangian coordinate S. It could be arc length parameter, for example. And actual is given here. Actual placement is given here. You have three vectors of rotations. And in certain sense is more or less general representation of beam in special description. I mean that three-dimensional, not plane deformations of the beam. And it looks like Kossara continuum. Okay, then we do the same operations. We introduce the strain energy for this. And what is the difference for considering this? The difference is very simple. This subindex C relates to curve. We have positions vector, rotations tensor. Instead of number operators, we have just a derivative with respect to, let's say, coordinate S. So we provide the same technique. We came to two vectorial strain measures, which looks like that. So instead of gradient here, you have simply just a derivative here. Instead of gradient, you have this. And this is nothing, formally, it's nothing new until now. It's nothing new. And kinetic energy also looks like in previous case. It's just a quadratic form of velocity, angular velocity. And we introduce another microinertia tensors here. So if you would like to see equation of motion, equations of motion looks absolutely the same form. We have this Piola-Kirchhoff stress and couple stress vectors and this kind of equations. And of course it's just one-dimensional counterpart of the three-dimensional case, of vice versa. And finally, as we have networks, networks consist of what? Network consists of fibers. For fibers we have a model which is Kossara curve. Joints. And as we already saw, with these joints, they could be massive. And here we assume such very crucial for the follow let's say, discussion, assumption that the fibers connected to joints rigidly. So it means that if you have joint and I have fiber, the angle between two, if I have another, let's say, fiber, this angle is fixed due to deformation. So this kind of, let's say, stuff is crucial assumption. Okay, to complete my model, we considered rigid body dynamics in exactly like in previous case. We have positions in reference placement and actual placement of any point, and any point, let's say we use some reference position like called pole, and so we have this representation, and this theta vector is just a rotation, because now we have only, let's say, translations in rotations. And description of the rigid body dynamics, it could be done like translation of one point and rotation about this point. So we have this. And finally, displacement vector looks like that, so we have this kind of stuff. And psi is just a vector of position of any arbitrary point in rigid body. No strain energy, everything is rigid, but we can introduce the kinetic energy. Kinetic energy is a gain, but kinetic energy, previous two formulations for kinetic constitutive equations looks like some axioms, because I just tell you I postulate it. Here it's derivable, we can derive it just having, let's say, mass point equations and consider standard definitions of kinetic energy, which looks like that. If I have this and you have distribution of the mass along the body, by the way, it could be inhomogeneous, and you have that. And if you substitute velocity, which we have here, which you represent like that in this formula, and integrate, we will see that this energy could be represented in some kind of, let's say, terms related. It became quadratic form with respect to the linear velocity and angular velocity with something, let's say, some coefficients. And we can introduce these coefficients, which is called inertia tensors, J, capital J, capital J1, and this tensor is Q-symmetric, the antisymmetric strain inertia tensor. And this guy is symmetric, and this is just a mass. And so finally we came to the same form, and I would say that in fact when you consider the Cassara continuum, typically it looks like that we know what we have in rigid body dynamics. We have this, and then we say that the same we have in Cassara continuum, but instead of mass we have density, instead of J we have another J, and so on. So this is kind of stuff. Okay, let me do some simplifications, because I have a lot of inertia tensors. I will say that this could be center of mass. So in this case J1 is equal to 0, and I have only one J here. So, and this J, by the way, is rotated, it should be Q, this Q. Okay, so it's in the equation of motion of this rigid body looks like that. We have this Newton law, and this for rotations, where is this total torque applied to the... Okay, we have everything. Now let us see what we have in elastic network. For elastic network we have, for example, such kind of network. We have rigid joint, we have something attached here. Okay, let us see how it looks. If you want, I can say that this is kind of a representative volume element. In what follows it became, let's say, just my point in Cassara continuum. Okay, so I will say that I have a lot of parameters. I have energy, kinetic energy, I have all ingredients. I have all ingredients and can write system of equations. Now you have, let's say, system equation for a lot of fibers, and now this prime is yes, its derivative is still derivative, but derivative is different directions. So you have S1, S2 and S3 different coordinates. And of course, for simplicity here it was used something like a Cartesian coordinates, so the standard Cartesian coordinates. So you have system of equations here, and also equations for joints. And the joints are numbered like that's I, J, K, something like that. So we will call it semi-discrete model, because it's not discrete, but discrete-like. We can write this equation of motion, and now what is important point in this, let's say, derivation, we should find some connection, kinematic compatibility between the points of, let's say, our Coursera curves and motion of our rigid bodies. And as we know that this is could be velocity of that point, contact point of Coursera curve attached to the rigid body. This is the velocity of the center of mass of rigid body. And this part related to rotations of this rigid body. This is for linear velocities. For angular velocities it's more simple. We have that they are simply equal. And what is xi here? Xi is a vector which is better to see. We have a lot of them, and that is very simple. You have center of mass, and this is the vectors going from center of the mass to center of mass of these, let's say, fibers. So it's just geometrical vectors. It should be small because it depends on the size of the, let's say, joint, but not. Okay, and equilibrium equations. Now this equation of motion and static compatibility conditions, dynamic connecting stresses and Cope stresses could be derived from variational principle, this least action principle which is formulated here. And here we use the same kinematic compatibility conditions in variational form. So for variations, we substitute it. It's very, let's say, formally it's not a big problem. In the case when you did it, we came to some effective continuum. And for static case, it looks this efficient energy of Coursera continuum depends on our strain measures in this form when vectors I, 2, 1 and so on is just directors, unit vectors along our fibers, and this is our strain measures. And of course it's somehow normalized. It's normalized with respect to volume of this, let's say. So in fact it means that we came to having enhanced strain energy of a beam. You have strain energy of effective medium for finding deformations. Let us see how we did it in the case of kinetic energy. In the case of kinetic energy of effective medium, first we introduce the mass. Effective mass looks like that. It's very simple. It's the simplest case because we just calculate the mass of all of elements. Mass of beams and mass of joint. Okay. Here volume also could be calculated like that, so everything could be depends on geometry. Then okay, what we are doing first with our energy. Kinetic energy in general consists of sum of such integrals from joint to joint, We replaced it using some trapezoidal rule, and the result we will have something related to values of this function Kc in joints. It's just in joints. Okay. Then what we should do? We should do the following stuff. Behind all this, it looks like nothing else like Hin-Mandel lemma when we compare it energy of effective medium and energy of our, let's say, element, but in some modifications related to some discretization. So if I consider discretization of my Coursera continuum, just integral, it became like a discrete sum taken in some points. It's exactly the same. So I compared two discretizations and we came to effective medium. Okay. Now this is nice formulas, but now for this case here we should substitute this, let's say, expression here, and we substitute expression, and we will get effective kinetic energy. Looks like that. This is V, our volume element, everything is combined here. And this summation relates to summation with respect to, let's say, this neighbors, which was shown somewhere here, to respect to these neighbors. This summation. In general, this could be generalized for any, let's say, connections, and also for, we will see that there is another presentation from our group from Cagliari when we discuss not flexible network, but something opposite, like a masonry. But in general, it looks, the approach is more or less the same. Okay, and finally, we can say that our effective kinetic energy looks like that when you have these microinertia tensors. And these microinertia tensors have some kind of, let's say, form which inherits the form of joint microinertia tensor of the curve, and also this part which relates to non-symmetry or symmetry of representation of connections of joints to the fibers. And so we can also calculate this tensor. Even we see that this tensor is skew-symmetric, because it's obvious that it's skew-symmetric. Okay, and of course we can do some kind of simplifications if you want. In which kind of simplification we can say that, first of all, I can say that, okay, I will neglect the mass of fibers. In this case, I can simply say, okay, this, let's say, will, for example, inertia should be disappeared. So I will have this, but this animal is still alive. To kill it, I should neglect totally the mass of fibers and the inertia of fibers, so that I became to, let's say, classical case when this effective microinertia tensor is like that, and this is 0. But in general, due to non-symmetry, this guy is not so symmetry. And let us see simple example when it could be important. We are speaking about nonlinear problems. There are very few problems which could be done analytically. We discuss propagation of so-called weak waves in this medium. Weak waves means that we have some discontinuity, and this discontinuity propagates. It's so-called acceleration wave, and this acceleration wave, in fact, it looks like a particular case of plane waves. And this brings us very simple technically simple, more or less, problem, algebraic problem. And this problem for these waves reduced to the following spectral problem when you have again this Q, and Q is a so-called acoustic tensor. This is a vector, okay, I'm using psi all the time. Psi now, this vector consisting of amplitude of translational wave and rotational wave, and this B. And this B became like that. It consists of this matrix with these tensorial elements, and you see that this tensor is not, it's fulfilled. Classical case looks like this is 0, this is 0. And so the problem became, in the classical, let's say, continuum, without this, the translational and rotational waves, they are decoupled. Here they coupled dynamically because of presence of this coupling J. So the main conclusion is shown here. So we have coupling between rotational and translational waves if this tensor is not 0. And by the way, it brings something, at least it seems, Okay, it should somebody decide, but in certain senses looks that we have something modification of symmetry material, because material could be behaves symmetric with respect translation in static case, and couplet in the case of dynamics. So we see this effect when you have considered waves. So that is some references, and thank you for your attention.
Thank you very much. And please.
Viktor, what will be changed if the joints will be not fixed?
If it will be changed, there is a price. The price will be that this is not possible to describe with micropolar elasticity, because for is micropolar elasticity, finally the basic idea looks like that. I have joint with some fibers. Okay, if I should discuss it, what is the primary variables? It's position of this joint and rotation of this joint and some connected deformations. If the fibers became, let's say, free, so you have more degrees of freedom. And this more degrees of freedom could be described in a different way.
A truss system
Okay, I can say that
classical.
it should be micromorphic model, but be careful in this statement, because in general I can imagine a lot of fibers connected to the point. More than, let's say, this number. And this it could be like multipolar, let's say, mechanics. So we have a lot of directors. Not three directors, but a lot of directors, independent fields. So it could be like...
Please.
My question is about the time derivative of this microinertia J. So this J was depending on this Xi, and the Xi beforehand, in which is the geometric from the mass, center of mass to the neighboring elements. And this is not changing in time, right? So this is in the reference configuration, or is it? Because you have later on used the rate of J.
Yes. Classical problem of rigid body dynamics consists of J depends on time. It depends because it depends on rotations. And so you can introduce reference J in reference, but it will rotate. It's rotation of the tensor. As a result, you have nonlinear equations of dynamics, even for a rigid body. So they became nonlinear. And analytically it could be solved in three cases, last case called after Sofia Kovalevskaya. First is Euler, Lagrange, and so on. So it became problem. If this problem is not exist, if this spherical is a ball tensor, yes, everything is not disappeared. But if not, you have troubles because it became nonlinear. You have nonlinear dynamics without any say in general.
Right. Which kind of applications are you going to perform?
In general, this application is obvious. You would like to model some networks, and networks like open cell phones and something like that. And the idea behind of that was like that some kind of harmonization brings, okay, nowadays exists also harmonization related to nonlinear deformations, but this is highly deformed structure, so you should consider finite deformations. And something, let's say, naive idea to say that, okay, I know that something for some particular element, I know I can measure the mass, okay, but I can measure perfectly, I can measure the mass, I can measure the property of this fiber element, and then let's see what is the effective medium for this. Something like that. So if I have energy of a beam of the fiber, I can say that what this is the energy of my continuum, somehow scaled and so on.
So the node, the joint is the brick.
No,
Yes.
here is interesting that, for example, static elastic properties depends on fibers. Nevertheless, dynamic properties essentially depends on fibers, geometry, and joints. If the joints is heavy, it could be dominant.
But was the question about application in mathematical or in
No,
practical?
No,
In
no.
No, in
So-
mathematical,
so
applications.
I changed your question. Can you earn money with this?
that's a very good question. But look, it depends on your, let's say, facility to earn money. In general, it's a good question, but it's something, let's say, behind of science.
No. Okay.
Because yes, okay, but I can answer you. Yes, we can got money because this was founded by DXG. So, it was written what we are doing, so it's okay. So I forget, I should send also to German Research Foundations for support.